In this guide, why time-based codes stopped password-only attacks and where they fall short. How the HMAC-based counter and 30-second window generate a reproducible 6-digit code. What TOTP enrollment and verification look like in an OAuth flow, and which attacks TOTP blocks versus which it doesn't. Identity Expert, powering you to be an expert in identity. Today we're covering TOTP, time-based one-time passwords. When you open Google Authenticator or Authy and see a 6-digit code counting down, that is TOTP in action. TOTP is defined in RFC 6238, which extends the HMAC-based one-time password algorithm of RFC 4226. The remarkable thing about TOTP is what it does not need: no network connection between your phone and the server. No real-time communication at all. Your phone and the server each compute the same 6-digit code independently, using two shared inputs, a secret key seeded during enrollment, and the current Unix timestamp divided into 30-second windows. They both run the same HMAC SHA-1 function. If the shared secret and the clock agree, the codes match. TOTP is the most widely deployed second-factor authentication mechanism on the internet. It is supported by every major authentication system. It's better than SMS, nothing travels over the phone network. But it has one fundamental limitation: the code itself is still phishable. By the end of this video, you'll understand exactly how the TOTP algorithm works, how enrollment and verification happen, and where TOTP sits in the broader MFA threat model. Here's the best analogy for TOTP: a combination lock that changes its combination every 30 seconds, synchronized to an atomic clock. Both you and the lock manufacturer have a copy of the master sequence, the shared secret. You both consult the same clock. At any given 30-second window, you both know what the current combination is. You enter it, the lock opens. Someone watching over your shoulder learns the current combination, but it's useless 12 seconds later when the window rolls over. And critically, no communication is required between you and the lock manufacturer during use. The secret was exchanged once during manufacturing. That's the enrollment step. After that, the synchronization is purely temporal. Both sides run the same algorithm at the same time. In TOTP terms, the shared secret is the QR code you scan when enrolling. The atomic clock is the Unix timestamp. The combination is the 6-digit TOTP code computed from HMAC SHA-1. The 30-second window is the time step defined in RFC 6238. The only weakness: if someone steals your secret or if a phishing proxy captures your code and replays it instantly, the magic breaks. TOTP protects against replay across time windows, but not against real-time relay. Let's be precise about what TOTP solves and what it doesn't. The problem it solves is static credential theft. Passwords can be captured through phishing, data breaches, or keyloggers and then used at any time in the future. The attacker has the credential permanently. TOTP adds a time-bound second factor. Even if the attacker steals the password, they cannot log in without the current TOTP code, which they don't have. And even if they somehow capture a TOTP code, say by shoulder surfing, that code expires in 30 seconds. The attack window is tiny. TOTP does not solve real-time phishing relay. If an attacker sets up a transparent proxy between the user and the real site, they can capture both the password and the live TOTP code and replay them to the real server before the 30-second window expires. This is called an attacker-in-the-middle attack, and it is the primary residual threat against TOTP. TOTP also does not solve the case where the shared secret itself is stolen. A breach of the server's TOTP secret database is equivalent to a breach of all TOTP credentials. This is why large deployments store TOTP secrets with the same care as password hashes, encrypted at rest, access logged, with HSM protection for high-value secrets. Let's walk through the TOTP algorithm precisely. TOTP is defined in RFC 6238 and builds on HOTP, HMAC-based one-time password, defined in RFC 4226. The algorithm has 4 steps. Step 1. Compute the time counter. Take the current Unix timestamp in seconds and divide by the time step 30 seconds by default. Floor the result. This gives you a counter that increments every 30 seconds and is the same on both the phone and the server at any given moment. Step 2. Compute HOTP. Run HMAC SHA-1 over the shared secret key and the time counter T as a big-endian 8-byte integer. The output is a 20-byte HMAC. Step 3. Dynamic truncation. Take the last nibble of the HMAC, the low-order 4 bits of the last byte, as an offset. Extract 4 bytes starting at that offset. Mask off the sign bit. The result is a 31-bit integer. Step 4. Compute the OTP. Take this integer modulo 10 to the power of digits 10 to the 6th for 6-digit codes. The result is the 6-digit TOTP code. Both the app and the server run this same computation. If the secrets and clocks are synchronized, the codes match. Servers typically accept codes for T-1 and T+1 as well to tolerate small clock skews. Let's look at how TOTP is deployed in practice. Enrollment uses the otpauth URI scheme. When a user enables TOTP in your application, you generate a random secret, typically 160 bits, base 32 encoded for compatibility with RFC 4648. You construct an otpauth URI, otpauth://tot, followed by the issuer and account name, with parameters including the secret, issuer, algorithm, digits, and period. This URI is encoded as a QR code and displayed to the user. They scan it with their Authenticator app. The app stores the secret. From this point forward, both sides compute codes independently. During verification, the user opens their app, reads the current code, and submits it alongside their password. Your server looks up the user's stored secret, computes the expected TOTP for the current time window and the adjacent windows, and compares. On a match, the login proceeds. An important security detail: the server should maintain a nonce list of recently used codes. Even within the same 30-second window, if a code has already been used successfully, reject it. This prevents replay attacks within the window. The TOTP shared secret is the most sensitive piece of credential data in your system. It must be encrypted at rest using a key encryption key, ideally stored in an HSM or a secrets manager. The TOTP threat model has three distinct attack vectors. The first is real-time phishing relay, also called an attacker-in-the-middle attack. An attacker sets up a convincing fake login page. When the user submits their username, password, and TOTP code, the attacker instantly relays all three credentials to the real site before the 30-second window expires. The attacker establishes a real session. TOTP cannot defend against this. The code is valid regardless of which site requested it. Only cryptographic origin binding, FIDO2, closes this attack class entirely. The second attack vector is TOTP secret database compromise. If the server's database of TOTP shared secrets is breached, the attacker has permanent access to all TOTP codes for all users, every code forever, not just one. This is why TOTP secrets must be treated as highly sensitive credentials and stored encrypted with an HSM-protected key. The third vector is time synchronization attack. TOTP relies on both sides having reasonably synchronized clocks. A sufficiently large clock skew would allow an attacker to pre-compute future codes or use expired ones. NTP synchronization and the standard window tolerance of plus or minus one step are the practical defenses. Overall, TOTP is a significant improvement over SMS OTP. The secret never travels over the phone network, but it remains phishable in real time. As of 2026, TOTP is the dominant second factor for consumer and enterprise deployments, but the trajectory is toward replacement by phishing-resistant alternatives. NIST SB 863b has formally deprecated SMS OTP, and its guidance positions FIDO2 passkeys as the target state for new deployments. TOTP is positioned as an acceptable transitional mechanism, better than SMS but not the end state. The practical reality is that TOTP remains widely used because it requires no special hardware, works offline, and has broad Authenticator app support across iOS, Android, and desktop. RFC 9048, the OATH TOTP algorithm, has clarified several ambiguities in the original RFC 6238, including stricter guidance on secret entropy and the recommended use of SHA 256 or SHA 512 instead of SHA 1 for new deployments. The default HMAC SHA 1 in RFC 6238 has no known practical weakness for TOTP specifically. The codes are too short to reverse the HMAC, but SHA 256 is preferred for new implementations. The long-term direction is clear. Passkeys eliminate the TOTP enrollment burden and the phishing vulnerability simultaneously. TOTP will remain in production for years, but for new greenfield deployments in 2026, passkeys are the first choice and TOTP is the fallback. All primary sources cited in today's guide are listed on screen. You'll find direct links to the RFCs and specifications in the video description below. If this breakdown helped you understand the topic better, please subscribe to Identity Expert. We publish a new protocol deep dive every week. Thanks for watching. If there's a specific identity standard, authentication flow, or security protocol you'd like us to cover next, drop it in the comments below. We build our content based on what the community asks for. Subscribe and hit the bell so you never miss an episode.